Okay, so the problem with this is that this is all very well and good and it's accurate, but there's something missing because according to this discussion, once a system is in a stationary state, an eigenstate, then it's not possible to have a transition between different eigenstates because there's no time evolution. Okay, so the probability density is constant in time, although it varies in space, but it's constant in time, and so there's no possibility of going from one eigenstate to another if the system is in an eigenstate already with this picture. Okay, and so in order to allow for transitions, in order to allow for the evolution of the system from one state to another, then we need to add something to the system. We have to add a perturbation to the system, and the perturbation can come in one of a number of forms. It can come as an electromagnetic radiation or an electric field. We can apply an electric field or electromagnetic radiation to the system. It could be a collision. The particles or the atom, for example, the hydrogen atom can collide with another hydrogen atom or something else, and that can create electric and magnetic fields and other forces that can perturb the system. You could even be vacuum fluctuations. That is, even if you have the particle completely isolated from its environment in a vacuum, okay, and it's in the dark, so there's no electromagnetic radiation. It's shielded from straight electric-magnetic fields, so there's no external fields. There's still something called vacuum fluctuations, which is a very deep concept related to virtual particles. Okay, so there's a vacuum energy, associated vacuum fluctuations, which can actually perturb the system, even if it's otherwise isolated. Okay, and that's actually that actually results in many interesting effects and important effects, such as spontaneous emission of atoms and molecules. Okay, so we need to add a perturbation to the system to allow for transitions. Okay, and so we need to develop the concept of time-dependent perturbation theory. So what we do is we start from a stationary state. We start in an eigenstate, psi sub n, and at some particular time we turn on a perturbation, okay, or a perturbation is turned on, and that perturbation lasts for a particular duration. Okay, so it's a perturbation in the sense that it is only on for a short period of time. It's not a constant. It's not something which is applied for a constant or a long duration. It's applied for a short duration, and in some sense, therefore, it's sort of a weak perturbation to the system. Okay, and in order to account for this perturbation, again, which can be an electric field, magnetic field, electromagnetic radiation, etc., we add in a new term to the Hamiltonian, which kind of gets added to the potential energy term in order to account for the perturbation to the system. Okay, so we add a new term into the Hamiltonian, and that's going to act, and it's only added for a certain period of time, and that's going to act on the wave function. And so what we have to realize is that if we start with a system which is in an eigenstate of the unperturbed Hamiltonian, and then we change the Hamiltonian at some particular time, the system, at least transiently, that is initially, is not in a stationary state. That is, it's not in an eigenstate of the new perturbed Hamiltonian. Okay, the new Hamiltonian that includes the perturbation term, because that's a different Hamiltonian. It has a different set of eigenfunctions, eigenstates. And since we started with the system in an eigenstate of the unperturbed Hamiltonian, then clearly when we change the Hamiltonian, at least transiently, the system can no longer be in an eigenstate of the perturbed Hamiltonian. Okay. So once the perturbation is turned off, okay, then the probability, then the system has evolved in time, okay, and the probability for finding the system in a different eigenstate of the unperturbed Hamiltonian, the Hamiltonian that you started with, it does not include the perturbation, is not zero. So you could have gone from psi n to psi m by the application of this perturbation.